Hello everyone, welcome to another lecture of the course Digital Signal Processing. In the previous lecture, we have seen the complexity of the Fourier Transform, and we saw that as the value of this n increases, the number of addition and multiplication required for computation increase drastically, and this leads to increase in the computation time. We also saw that we need a faster implementation algorithm for this Fourier transform. So let us try to develop some kind of mechanism that would lead to a faster implementation. So for that, let us initially consider this DFT equation, and now what we will do is we will just split this equation into two summations, where first this n is even and this n is, and the second in which this n is odd. So what we have is summation where this n is even x of n wn to the power kn plus summation where this n is odd x of n wn to the power kn. Now what we can do is we can just replace this n by 2n and vary it from 0 to n by 2 minus 1. So we can do it because what we are considering is this n means we know that this n is ranging from 0 to n minus 1. So we are having total n values. So what we consider is the n by 2 values are even. So we have n by 2 even values and n by 2 odd values. So if we replace this n here and here by 2n, so this n would, so the new n would be varying from 0 to n by 2 minus 1. So what we have is summation n running from 0 to n by 2 minus 1 x of 2n wn to the power k into 2n plus summation n running from 0 to n by 2 minus 1, and now as we have odd value of n here, so we would be considering it as 2n plus 1 wn to the power k 2n plus 1. So we have this here. Now if we look at this twiddle factor here, so using the radix property, what we can do is we can just write it as wn by 2 to the power kn. Similarly, if we consider this twiddle factor here, we can write it as wn to the power 2 kn multiplied by wn to the power k, and again this can be written as wn by 2 to the power kn, and we know that we can do this because radix property for twiddle factor. So if we do that, what we can simplify is something like this. So we have x of k is equal to summation n running from 0 to n by 2 minus 1 x of 2n wn by 2 to the power kn plus we have this wn to the power k, and it is constant with respect to n, so it can be taken outside the summation. So it is summation n running from 0 to n by 2 minus 1 x of 2n plus 1 into wn by 2 to the power kn. Now if we observe these summations here and here, so if we observe these two summations, both of these are n by 2 point DFTs. So these two summations individually are n by 2 point DFTs, and this first n by 2 point DFT is obtained when we consider the value of n, only the even values of n, and this second n by 2 point DFT we obtain when we consider only the odd values of n. So what we will do is we will just represent these two summations as x even of k, where we consider the even values of n, plus wn to the power k and x odd of k. So we have something like this: x of k is x even of k plus wn to the power k x odd of k, where this x even of k is given as summation n running from 0 to n by 2 minus 1 x of 2n wn by 2 to the power kn, and x odd of k is given as summation n running from 0 to n by 2 minus 1 x of 2n plus 1 wn by 2 to the power kn. Now we know that these two are n by 2 point DFTs, which means that both of them would be periodic with respect to n by 2. So as these both are n by 2 point DFTs, so they would be periodic with respect to period n by 2. And moreover, as these are n by 2 point DFTs, this k will also be ranging from 0, 1 and so on till n by 2 minus 1 only. Which means that if we consider these two summations in order to find this x of k, we are just going to get only n by 2 values of this x of k, whereas initially we have in total n values. So what we are getting is only half of the values that we have. But in order to get the next half of the values, what we will consider is we will make this argument as k plus n by 2. That is, we will start from n by 2 onwards and then go on adding one term there. So what we will do is we will find x of k plus n by 2, which would be giving us the next half values, that is next n by 2 values. So it would be given as x even of k plus n by 2 plus wn to the power k plus n by 2 into x odd of k plus n by 2. And we just said that these two summations, that is these two DFTs, are periodic with period n by 2, which means that this x even of k plus n by 2 would be equal to x even of k, and this x odd of k plus n by 2 would be equal to x odd of k. So this can be written as x even of k, and this can be written as x odd of k. Now we have seen the symmetry property for this twiddle factor, and we saw that if we have wn to the power k plus n by 2, it would be equal to minus wn to the power k. So we have it as minus wn to the power k, and this is because of symmetric property of wn to the power k. So now we have two equations, something like this. So we have x of k equal to x even of k plus wn to the power k x odd of k, and x k plus n by 2 x even of k minus wn to the power k x odd of k. So this gives us the first n by 2 values, and this gives us the next n by 2 values. Now we can represent these two equations in some typical structure, which can be drawn something like this. So let us consider this x even of k and x odd of k, and we know that using these 2 points we need to find x of k and x of k plus n by 2. Now if we observe here, if we need to find the value of this x of k, we are going to just consider this entire thing as it is. So we have it like this. So if we need to find this x of k, we are going to just consider this x even of k, which is scaled by a factor simple 1, whereas we are going to add this factor wn to the power k into x odd of k, means this x odd of k has to be scaled by a factor of wn to the power k. So this is the scaling factor, and once it is scaled, then we are going to just add it here. So what we are getting here is x even of k, which is scaled by a factor of 1, and x odd of k, which is scaled by a factor of wn to the power k, which is going to be added here. So this point here will be simply indicating addition. So we have it like this, wn to the power k into x odd of k. Now if we need to find the value of this x of k plus n by 2, then at that point again we have this x even of k as it is. So we have this x even of k as it is, but when we need to consider this x odd of k scaled by wn to the power k, it is with a negative sign. So we need an extra scaling of -1 here. So that would lead to x even of k added with minus of wn to the power k into x odd of k. So what we are obtaining here is x even of k minus wn to the power k into x odd of k. And this structure is known as the butterfly structure. Another point to be noted here is, if we observe this xe of k and x odd of k and observe this factor here, that is x of 2n and x of 2n minus 1. So this x of 2n, this 2n factor simply represents decimation of x of n by a factor of 2. And as we are decimating in the time domain, this DFT implementation is known as decimation in time fast Fourier transform with radix 2. So this implementation is known as decimation in time fast Fourier transform, and as this factor here is 2, so we are considering the radix as 2. So this is decimation in time fast Fourier transform with radix 2, and it is also known as, or it can also be written as DIT-FFT. So this is decimation in time fast Fourier transform. And this is the butterfly structure for this DIT-FFT, and we are going to use this structure in the further lectures in order to solve some examples where we will consider different values of n. But now let us try to understand this entire mathematical process with example of for n equal to 4. So what we will do is, we will consider this entire process for a specific value of n in order to understand everything much clear. So let us take n equal to 4. So if we consider the initial DFT equation, so that can be written as summation n running from 0 to 3 x of n wn to the power w4 to the power kn. Now we need to just split it into even parts. So this is the even part here, and this second summation is for the odd. So we consider the value of n as 0 and 2 here, and n as 1 and 3 here, and we know that we can just represent it by substituting this n here and here by 2n as we are considering the even part. So it is summation n running from 0 to 1 x of 2n wn n by 2, so it would be 4 by 2 to the power kn plus w4 to the power k into summation n running from 0 to n by 2 minus 1, so it would be 2 minus 1, that is 1, x of 2n into w2 to the power kn. So again this is the even part and this is the odd part, so we can write it as x even of k plus w4 to the power k x odd of k. So this is what we have here, and again we had seen here that we can just shift this x of k by n by 2 factor so as to get the next n by 2 values. So same thing we are doing here. So when we do that, at that point this x of k plus n by 2, that is this 2 here, is n by 2, which is equal to 4 by 2, which is equal to 2. So this x plus 2 can be given as x even of k minus w4 to the power k x odd of k. So this follows from the previous derivation what we have obtained here. So same thing we have considered for the specific value of n equal to 4, and we had seen that this x even of k is given by this equation and this x odd of k is given by this equation. Now we know that these two are n by 2 point DFTs, which means that if we consider the initial n as 4, so we would be having it as a 2 point DFT. Similarly, this would also be a 2 point DFT, which means that we can again split these two further so that we get 1 point DFT. So what we can do is we can just split this xe of k. So this xe of k can be further split into two parts, that is x even of k, that is just considering this even and odd components for the value of n here, and we would be having x odd of k. Similarly, this x odd of k can be split into again two parts, that would be x odd even of k and x odd of k. So let us first consider this part here. So we had found that x even of k is given as summation n running from 0 to 1 x of 2n w2 to the power k 2 to the power kn. So now we can, when we split it into two parts, so at that point this, for even this n is to be substituted by 2n, and for odd part this n is to be substituted by 2n minus 1. So when we are going to find it for even, we need to go for n to be substituted as 2n, and when we go for finding the odd part, we need to go for n to be substituted by 2n plus 1, and when we do that, what we obtain is this summation n running from 0 to 0. So now this 0 we are obtaining by considering 2 by 2 minus 1, that is this initially this was a 2 point DFT. So we need to consider 2 by 2 minus 1, so that would be 0, w n by 2, that is 1 to the power kn, and summation n running from 0 to 0 x of 2 into 2n plus 1 w n to the power kn w2 to the power k. So this can be reduced further like this, and when we substitute the value of n as 0, we can see that only one value is to be substituted of n. So if we substitute n as 0, so what we obtain is x0 w1 to the power 0 plus x2 w1 to the power 0 into w2 to the power k. So the even part x even of k can be written like this. Now what we can observe is this is the even part of this xe of k, so we can just write it as x even of k plus this w2 to the power k as it is, and this part can be written as the odd part of this x even of k, so it can be written as x even odd of k. So we have it like this xe of k is equal to x even k plus w2 to the power k into xeo k, and this xe plus k plus 2 by 2. So we had seen it previously that in order to find the next n by 2 values, we add it here. So we have xe of k plus 1 is given as xe ek minus w2 to the power k xe odd of k, and we saw that this xee of k is given as x of 0 and this xeo of k is given as x of 2. Now let us repeat the same exercise for the odd part. So we have it initially like this, and we can just split it again into two parts. So for even we just substitute n as 2n, and for odd we just substitute this n by 2n plus 1, and when we do that we obtain the equation like this, and again the limits of n would be from 0 to 2 by 2 minus 1, that would be again 0 for here as well as for odd part. So for even as well as for odd part, and when we simplify it and substitute the value of n as 0 in both the equations, what we obtain is x1 w1 to the power 0 plus x3 w1 to the power 0 into w2 to the power k. And again what we can observe is this part here is basically the even part of this initial odd component, so it can be written as xoe of k, and this is the odd part of this initial odd component, so it can be written as xoo of k. So what we have is something like this. So this x odd of k is xoe of k plus w to 2 to the power k x odd of k, and again we can find the next n by 2 values by considering this factor of n by 2 here. So it is x odd of k plus 1 is equal to x odd even of k minus w2 to the power k into x odd of k, where these two values are found like this. So now if we observe carefully these values and these values here, so these are 1 point DFTs, and 1 point DFT is simply that the initial signal itself, that is if we have say x of some value x of n equal to say 1, then its DFT, that is x of k, would be equal to x of n, which would be equal to 1 itself. Means 1 point DFT would be the signal value itself. So now if we have, by splitting initial DFT, go on splitting it till 1 point DFT, what we are left with is the signal value itself. So what I am saying is something like this. So initially here we had this 4 point DFTs, then we go on splitting it into the even and odd parts, and then we get 2 point DFTs, and then again we just go on splitting further and get single point DFTs, that is 1 point DFT. And we saw that this 1 point DFT are the initial signal values itself. But initially we are supplied with this signal values, and we need to get the value of this x of k, and therefore we need to perform a back tracing from signal values to this x of k. That is, using this signal values that are our initial 1 point DFT, we need to go for finding out the 2 point DFTs, and then go on for finding the 4 point DFTs, and if we have the value of n higher, then we need to move one or more steps more ahead. So this back tracing can be considered like this. So we had seen that this xee of 0 was x of 0, this xeo of 0 was x of 2, this xoe of 0 was x of 1, and this xoo of 0 was x of 2. Now this even part was constructed using this xee of 0 plus w2 to the power k into xeo of 0, that is these two components, and it is simply addition of them. So what we have is this factor here and this factor here is used for calculation of this even component here, and we can see that we have an additional scaling factor of w2 to the power 0. Similarly, this x even of 1 is calculated from this x of 0 and x of 2 with again some scaling factor here. So what we have it as, we consider it like this. So we have this x of 0 and this x of 2, and again we are having a scaling factor of minus w2 to the power 0. Similarly, if we observe here, this x odd of 0 is constructed using this x of 1 and this x of 2, so here it should be 2, sorry, here it should be 3. So this x odd of 0 is constructed using this x of 1 and x of 3, so it can be represented like this. This x1 is as it is, and then we have this x of 3, but again we are having a scaling factor of w2 to the power 0. Similarly, this x odd of 1 is constructed using this x of 1 and x of 3, but with a scaling factor of minus w2 to the power 0. So we have it something like this. So this x of 0 is considered as it is, x of 1 is considered as it is, and then we have this x of 3 with a scaling factor of minus w2 to the power 0. Now if we observe, now we have obtained these 2-point DFTs. So from this 1-point DFTs we have obtained these 2-point DFT values. Now using these 2-point DFTs we need to obtain the final sequence of this x of k. So if we observe this x of 0, it is basically obtained from x even of 0 and x odd of 0, that is this point here as well as this point here. So this is zero here. So this x of 0 is obtained from x e of 0 as well as this x odd of 0. So what we need to do is, we need to consider it like this. So we have this x e of 0 and then we have this x odd of 0, and what we observe is the scaling factor is w4 to the power 0. If we consider this x1 of 0, we have this x e of 1, that is this point here, and this x odd of 1, that is this point here, with a scaling factor of w4 to the power 1. So we can consider it like this. So it is x e of 1 and x odd of 1 with a scaling factor of w4 to the power 1. Now again if we consider this point x of 2 here, it is constructed using x e of 0 and x o of 0, but now the scaling factor is minus w4 to the power 0. So we have it like this. We have this x e of 0 and x odd of 0, and the scaling factor is given as minus w4 to the power 0. Similarly, if we consider this x of 3, so it is x e of 1, that is this point here, and x o of 1, that is this point here, and now we have the scaling factor of minus w4 to the power 1. So we have it something like this. This point here, that is x e of 1, and this x o of 1, but with a scaling factor of minus w4 to the power 1. So what we observe is, initially we had these points and now we are going on back tracing the values in order to obtain the DFT sequence. So the DFT sequence that we obtain is x of 0, x of 1, x of 2, x of 3. But in order to obtain this sequence, the sequence of initial signal in the time domain is somewhat changed. Means instead of x of 0, x of 1, x of 2, x of 3, we are considering x of 0, x of 2, x of 1 and x of 3. Now there is some kind of pattern that we are observing here. So let us try to analyze that pattern. So we have the value of n as 0, 1, 2, 3 and the original sequence that we are given. So the original sequence that we are given is x of 0, x of 1, x of 2 and x of 3. Now if we consider this representation of this n in the binary form, so it can be 0, 0, 0, 1, 1, 0 and 1, 1. That is, the highest value of n, that is 3, can be simply represented by 2 bits. So it is given by 1, 1 here. Now if we consider the bit reversed order of these binary patterns, so they can be given as like this. So the bit reversed form of this 0, 0 would be simply this 0 here and this 0 this side. So it would be simply 0, 0, which is again in decimal 0. But the bit reversed format of this 0, 1 is simply given by this 1 would be placed before this 0. So just change the position of these. So it can be given by 1, 0 here. So that would be equal to 2. Now the bit reversed format of this factor here, that is 1, 0, is simply this 0 would be first and then we would be having this 1. So it is given as 1. And the bit reversed format of this 1, 1 is again 1, 1, which is equal to 3. So what we have, the new sequence is x of 0, x of 2, x of 1 and x of 3. Now if we observe the sequence that we had considered in order to find this DFT is x of 0, x of 2, x of 1 and x of 3, which is exactly same that we obtain when we just bit reverse the value of this n or just bit reverse the argument. So this bit reverse sequence is to be considered in order to find the DFT. So the initial step would be considering the binary form of this n and just perform bit reversal. Now if we need to have this binary form, then we would be requiring some number of bits, which means that the number of bits that would be considered would be like 1 bit, 2 bit or 3 bit, and depending on that the value of n would be changing. That is, suppose if we have the value of n from 0 to 5, then this 5 can be represented using 3 bits, which means that all the numbers from 0 to 5 are to be represented using 3 bits. And we know that if we have 3 bits, then in total we would be having 2 to the power 3 values. Which means that when we bit reverse them, like this 0, 0, 0 would be 0, 0, 0, then this 0, 0, 1, which is 1, would be 1, 0, 0, then 0, 1, 0 would be simply 0, 1, 0. If we consider 0, 1, 1, then it would be 1, 1, 0. Now this 1, 1, 0 is basically 6, but my value of n is only from 0 to 5, which means that this x of 6 is to be substituted as 0. Now if we need to substitute it as 0, which means that we need to consider the value of this x of n for a range of 0 to 2 to the power 3 minus 1, that is total 2 to the power 3 values of x of n should be considered. So what I mean to say here is the minimum number of bits that are required to represent the highest value of this argument, that is 5, is to be seen, and accordingly the value of n is to be considered. Or in other words, the value of n should be found as 2 to the power m, where this m is the number of bits or the minimum number of bits required so that we can represent the highest number, that is 5, or any highest number for the argument of that signal, or the highest value of this n that we have. So now if we are having a given length of signal, for example, the example that we had considered was n ranging from 0 to 5 for this x of n. So the length of this signal is basically 6, and we need to find the number of bits required. So those can be found out by just considering log to the base 2 of L, but with a seal here. And once we have the value of this number of bits, that is m, then the value of n is to be chosen as 2 to the power m. So this choice of n has to be done initially, which depends on the length of the signal. So in this lecture we have tried to implement an algorithm, or tried to derive an algorithm for faster implementation of the Fourier transform, in which what we did is we just split the initial Fourier transform equation into two parts, considering the n as even and n as odd. So we get these two expressions, and when we solve it, we are left with these two terms here, that is obtained from xe of k and x odd of k, where this x even of k is given by this formula and x odd of k is given by this formula. And then we saw that this range of k is now restricted from 0 to n by 2 minus 1. So in order to obtain the next n by 2 points, what we do is we consider x of k plus n by 2, and then further solving we obtain this equation. So we claim that using these two equations we can find all the n values of x of k, that is the n-point DFT. We also saw the butterfly structure that is used for representation of this x of k, or which can be easily used for finding the value of x of k and x of k plus n by 2 once we have the value of this x even of k and x odd of k. Then we considered a specific case of n equal to 4 and repeated the same process in order to understand it better, and we saw that when we go on splitting this x of k in further, so till we get this 1-point DFT, then at the end when we are having this 1-point DFT, we are just left with the initial signal value itself, which means that we can just go on splitting everything, the entire DFT sequence, till we are left with a single point DFT, and this single point DFT is nothing but the initial time domain signal. And we know that we need to find this x of k from this given sequence. So we need to just trace backwards in order to obtain this x of k, something like this. So from this initial sequence that we are having, we need to just perform some kind of back tracing depending on the equations that we have, and then find the value of this 2-point DFTs, then go for this 4-point DFTs, and if we have more the value of n higher than 4, then we need to have another stages, and so on. So starting from the single point DFT, then 2-point DFT, then combine it further to obtain the 4-point DFT. So such a back tracing is required to obtain the entire DFT sequence. So this is what we saw here, and another observation that we made was on the sequence or the rearrangement of the x of n values. So we observed that the original sequence was x0, x1, x2, x3, but the new sequence that is to be considered while finding the DFT is of the order of bit reversed. That is, this argument here, that is n, should be bit reversed. That is, initially we need to represent this n in the binary form, and then just simply bit reverse them and find the new argument in the decimal form and then just rearrange the entire sequence. Now what we saw that the rearrangement of entire sequence has to be done properly and is dependent on, and as we know that there are some minimum number of bits required to represent any number. So suppose we are given with a range of n from 0 to 5, then this 5 can be represented with a minimum bits of 3. So 3 is the minimum bits, and this can be found using the formula m equal to ceil of log L to the base 2, where this L is the length of this sequence here, length of the signal that we are given. So why do we need to do this is because if we consider the bit reversal, then we may get a value that exceeds this 5, and at that point we may not have the value of x of n. And we had initially seen that we obtain inherent periodicity when we perform discretization of omega. So in order to consider the values after this as 0, so as to obtain proper DFT, we need to choose this value of n properly, and in order to avoid any kind of ambiguity in the result and wrong calculations, we need to choose this n at least equal to 2 to the power m. So this creates a restriction in choosing the value of m here. So in this lecture we saw the decimation in time fast Fourier transform. In the subsequent lecture we would look at few examples. So we would be considering the example for n equal to 4 and n equal to 8. So let's stop here. Thank you.